G'day. For longer than I'd like to remember, I've had this sitting around my shed. This is a casting for a Hercus Rotary Table. It was given to me in return for some machining work, and I've had it here, been meaning to do something with it, never quite got round to it. Every so often I get a reminder, and I thought, oh yeah, better do that. Anyway, today I finally got off my bum and did something. And so this is about making a couple of parts which are needed for this, courtesy of a drawing by my friend Bob over in the West, and then showing you how a rotary table basically functions. So you'll see a little bit of machining, and you'll also understand a little bit more about how a rotary table works. The first part I'm doing is this. This is the shaft that goes up the middle of the eccentric bush, and nothing terribly tricky here except that there's a step here. So what I've had to come in with my parting tool and plunge in here to take this down to the final size. Then I'm coming in with a normal turning tool to bring that down. So that's something you can do if you've got a step, flange, whatever in the way on a shaft like this. I'm working from this end through because if I took this off first and then worried about doing this bit, this could flop around a bit. And so working from right to left here, so I'm taking this down to size, and then there's a reduced portion up here with another thread on it, so that'll be the last thing I do. Then I'll part off. I might do the threads in the lathe here, certainly not single point cutting them with a die, but I can do that once the part is parted off. There's the shaft. Well, all the turning work is done. I need to put a couple of flats on the sides here, and there needs to be a keyway in there for the worm to go onto. I looked in my box of bits, and strange enough, I do have a keyway, a Woodruff key the right size for that, so that saves me making one. Just a comment on this piece of shaft here. This goes into the bore of an eccentric bush. Now, steel on steel is not a good mix, but at slow speed, so it'll do it. It might sound a bit gritty. Two ways around this. One is to put a bit of grease on here, or some oil, but the plans I have actually have some oil grooves there. Now, I haven't put those on there because I'm not quite sure what sort of fit I've got. This is about half a thou under the nominal bore, and I'll try and remount the bore so it should be a nice fit, but we'll see how we go. However, one thing with these sorts of parts is that you don't want to actually have too good a finish on here, because you want somewhere with the oil to grab and stick to. So just remember that if you're ever doing a shaft in a sleeve arrangement, that while you want, if you've got a brass bearing or something, you want a nice smooth finish there, but at the same time you want something that's going to hold the oil. So I may have to come back and put an oil groove on there. I'm up to making this bit now. Now, once again, this is pretty straightforward turning, just a number of diameters, but the difference between this diameter and that one are offset by an amount of eccentricity. So what I've done is I've turned down to this outer diameter, right? I've left this on here for the moment, but that becomes my reference diameter, and I've got that sitting up in the 4-jaw chuck here. I've started by dialing it in so it's running on center, and to hold the back on, I've got this wooden plug, which you've probably seen before, but that just sort of sits on the center like so. And now that I've got this dialed in, I can now offset that. One of the things you have to remember too is that the offset here is 0.09375 inches, sorry, so 93.75 thou, okay, but if you're going to read that with a dial indicator, it's actually going to be double that, right, because if you can imagine, as the center point moves 1 unit, the outside is going to move 1 unit this way, but this side is going to move 1 unit this way as well, and so you'll see 2 units here for 1 unit worth of movement. So just a trick when setting up. I'm using my universal indicator because this is one of the things that I want to be able to do with it. So I need to set this over. One of the first things I'll then do is drill a center in here so that I've got a bit better support, because with this being offset there's going to be a bit of eccentricity there. And that way I can then turn down these diameters without any great dramas. I've measured the hole that this goes into, and that's 1.003 inches, which means that if I make this 1 inch as per the drawing, or maybe just a little bit bigger, that should be a nice fit in there. It's probably a good idea to do that when you're doing this sort of fitting, particularly when something you haven't made, just because if they've worked on the basis that the hole is to size and the shaft is going to be under, and you make it on the basis of the shaft is to size and the hole is going to be over, you know, you may run into a few problems and have to redo things. There's my eccentric and the little lead-in bore. I've now got to turn this around, put the hole through the middle, neaten up the corners here and put a reduced diameter on the other side. That one's only 3/4 of an inch, this one's an inch, and so I figured I'd prefer to hang on to this to put that on rather than to hang on to that to put this on, and that's why I left that large to start with. So I need to redial this, but that's the end of this setup, and I don't like leaving setups overnight. Couple of reasons there. One is the night shift can sometimes be a little bit mischievous, shall we say, and so change things on you if you're not careful. But the other one is that, you know, who knows what can happen overnight with clamps relaxing, with things moving, all that sort of thing. So if you have to leave a setup overnight, then yeah, you probably need to check everything's tight, everything's where it should be, and all that sort of thing. But in this case, I finished with this. I can now flip this around in the morning and start on the other end. I've just trued this back up in the chuck. It doesn't really matter, because after all you're wanting this diameter to be on axis, but I find that if I have the eccentricity pointing it directly at one chuck jaw, it makes it a little bit easier, because these two jaws you know, basically come in equal amounts, and the other one comes in, you know, a little bit more, the other one comes a little bit less. Just to make it a little easier. If you had it so that the eccentricity was, say, pointing that way, you'd have to juggle two pairs of jaws, so just something to bear in mind there. I've just started drilling out the central hole here, and I'm starting with a 7/16 drill, and just because that's the first drill that came to hand of a decent diameter with a decent length. This is actually a long series drill. and I'm finding that the Australian hardware shops these days are stocking long series drills. You do have to remember with these though that they're still, you know, once you get beyond sort of 5 diameters or so, you still need to bring it out and clear the chips, because although the flutes will clear the chips to a degree, they get, you know, hung up around about that 5, somewhere between the 5 and the 5 diameter range. They start to clog, and so you need to pull it out, give it a flick with your brush, apply a little bit more lubricant if you're using that, and off you go again. As you just saw, I cut the Woodruff key slot in the bottom of the shaft here using my extended V-block, and then I've come along and put the flats on the side of the head here. That's where the pointer for the dividing plates rests, but also is one way of doing the handle for the end of the rotary table. So that's that one done. On the other one, I had to put a slot in and a hole for an oil point. The plans call for an oil hole 30 degrees off sort of the main axis. Finding that is a bit tricky, and I've been racking my brains to try and work out how to do it, and so this is what I've come up with. I've got a V-block in here, and I've centered up the axis of the mill on the V-block, so the middle of the V is the axis of the mill. I normally use this for finding edges and things like that, but it also will work on in the Z direction. I've never quite worked out, you know, how to do that satisfactorily, but that's one of the things that we'll do. I've got this set up so I can find the maximum, shall we say, lobe height here. So I've done that, and that's about there somewhere, and I've put a texture mark on there to mark that spot. Now, because it's a cylindrical surface, the ball is going to want to slide either way. So you need to do this from both directions and work out where you think it is. You can see the needle jump there a little bit. But anyway, that's where I'm saying it is. And so from that, and using trig on that, I worked out that the 30 degrees is equivalent to 9.86 millimeters. So what I'm going to do is mark that spot there, and then using a set of calipers, come down that much, mark that, and that's going to be my 30 degree spot where I can drill a hole. And I can set that up in here without too many dramas. The last feature I need to put on is this slot. You can see it a bit there, and you can see it a bit here. I was a bit stuck on how to position that, but then I worked out that, well, the oil hole is actually 60 degrees from the slot. So what I did was I put a pin in that oil hole and then lined that up using one of my 60 degree squares, so that was hanging down, and that's going to be good enough for that slot. That slot is for a bolt to limit travel, so I can't see any problem with that. This is the basic rotary table casting, and the table sits in here. There's a ring gear bolted to it, so that goes in like so. And over here there are a couple of cotters that clamp on the inside of the table, so when you want to lock the table up, that's what you use for doing that. Over here, there's my shaft. I did put some oil grooves in it, and that goes in like so. And if I can get this right, for some strange reason it seems to go on easier from one end than the other, even though it shouldn't. Okay, but you can see there's the shaft with the flats rotating the worm. And this is what makes, I mean, basically this is how a lot of rotary tables work. So, you know, don't think, oh well, this is a special one. But you might be able to see just in here how when I rotate that, the teeth engage, and that's how you get the low backlash in a rotary table. You rotate this part until the teeth engage there. There's another cotter which goes in here, and so once you've got that in place, you lock that up. Now most rotary tables work this way, or have this basic principle behind them. I mean, how they lock and all that sort of thing varies from table to table. The slot that was cut into here is for controlling the rotation of this part so it doesn't over-rotate and disengage or whatever. So that's what that's for. So anyway, that's how a rotary table works, and as you can see, even though this one isn't centered, if I rotate the shaft there, the worm turns, the worm gear rotates, and so the table on top is going to rotate. So that's about all I've got time for this week. Thanks for watching. See you for the next one.